Good morning, afternoon, evening, middle of the night, depending on your time zone. Welcome to Community Central Tech Tuesdays. For this special Red Hat Summit edition of Community Central, we are going to be sharing a relatively new project, one in the security space and trusted computing. We have with us Nathaniel and Mike, who are going to tell us all about it. Before we get started, for people who are dialing into Community Central for the first time, on your screen, browser, app, depending on how you're attending, there should be a question and answer pane. Mike and Nathaniel will be taking questions at the end of their presentation. Please put your questions in that pane. And for that matter, look at other people's questions that pane and upvote them. At the end of the presentation, we will be taking the most popular questions on tape. And as always, this is being recorded, being shared on the Red Hat community YouTube channel. So if you do miss any pieces of it, you will be able to go back and watch that recording later on today. And that said, Nathaniel and Mike, I have one question. Enarx? Is that how it's pronounced?
It is pronounced that way. You're going to ask what it means now?
No, I figured you'd get to that.
Okay, well, I'm going to let Nathaniel start then. You start with the Enarx name, Nathaniel, and we'll take it from there.
Yeah, so the Enarx name is a fake Latin word, which means within the castle.
That makes sense.
Yeah, and one of the key concepts that we'll be talking about is a keep, the place you defend and which provides you with the highest security we can provide. So that's kind of how it came up. Both Nathaniel and I are kind of ancient language geeks as well as lots of other type of geeks. So yeah, thank you, Josh. Appreciate it. So yeah, first of all, I'd like to say thanks to everyone for coming. We really appreciate your time. For those of you watching live, you're about to get an hour early preview of some information that we will be sharing officially at Summit for the first time, but Summit has started. So we don't feel too bad about this, and we really appreciate your joining us. So I'm going to share my screen, and we will start off, if I can do this. Okay, so hopefully you are now seeing my screen.
It's there.
I do see it.
Excellent. Well, that's a pretty good start. Let's hope everyone else can as well. And as Josh said, please ask us questions, and we will try and answer them at the end. Put them in the bar. So let's start with the problem. So let's say you are in banking and finance. You've got lots of data that you need to keep safe, whether it's customer data or your banking information, or how much information people have in their credit card accounts, whatever it may be. Well, the same goes for government and public sector. In fact, there's lots of information to do with citizens that you want to be keeping safe, or government policy, and in fact for telco. So let's say billing records or routing records, or all of those sorts of things. And in fact, for every single sector we can think of, there are real requirements for confidentiality and integrity. And to be clear, by confidentiality, we mean stopping people seeing what you've got. And by integrity, we mean stopping people changing what you've got. So whether it's HIPAA, which is US healthcare requirements, or GDPR, which is European and I guess worldwide data requirements more generally, or just sensitive enterprise functions. Maybe it's stuff like your firewall configurations or your routing configurations, or frankly, things like your CEO's payroll data, which I guess you don't want to be leaking to anyone. Defense, there have even been some really interesting stories about human rights NGOs being attacked by, should we say, government-sponsored agencies to get information about some of the things going on. So the point is that everybody has a need for confidentiality and integrity, and it's not managed well right now. So, Nathaniel, do you want to explain what this is?
Sure. So this is a fairly traditional virtualization stack where you've got a CPU on the bottom and a BIOS and a firmware, hypervisor, bootloader, kernel, space middleware, and an application at the top. Should be pretty familiar to everyone here. And what I do want to point out is the colors represent trust relationships. So you'll notice that there's a large section in the middle, and this is typically the kind of mono stack that has been delivered by companies like Red Hat in the past. And the idea is essentially if you can get most of your stack from the same place, then you reduce the number of trust relationships that you have. And the benefit of showing it this way is that even if you go with a complete stack, you're still not eliminating all of the trust relationships that you have, and they can be rather complex. And this actually gets even worse when we go to containers. Mike, you want to go to the next slide? Because you're actually dividing up the stack in even more ways, and you have trust relationships coming from multiple different places. And this is something that we have taken to be a problem. And I think we have comic on the next slide, Mike.
Yeah, I was going to say actually before we get there that it's not just you have to trust that the people providing these have done a good job of engineering them and that they are trustworthy. It's also that you can trust that none of them gets compromised in as you're actually running your application at the top. What we're talking here is about protecting that application at the top from basically any of the layers below it, because any of them could be messing. And yeah, here's a very nice XKCD comic, which kind of gives you an idea of hopefully you don't have all of these problems, but it kind of plays with the layers issue we were talking about earlier on. So Nathaniel, why don't you talk a bit about TEEs? They're pretty cool.
Yeah. So the idea of a TEE is basically to isolate essentially the top two layers in a hardware-enforced isolation. We call this in Enarx a keep, but TEE stands for Trusted Execution Environment, which is the broader industry term. And the point is that those top two layers get isolated from the rest of the stack, and the rest of the stack could be compromised, but they can't penetrate into those top two layers.
So in a TE, basically the only thing that has access to those two layers is the CPU. What happens if any of the other layers try to access it? Well, they are blocked by the CPU. What do we mean by that? Well, basically, the CPU is providing some encrypted memory pages to allow you to run your application and the middleware associated with it in such a way that nobody else, even if they have root access, kernel access, whatever, can look inside and can make changes. So one way to look at it is that you have a protected area within the host, which you can use for execution of sensitive workloads. That's kind of what a TEE is. And again, Nathaniel, why don't you explain what some of these things are and why they're important?
Sure. So we start off on the left-hand side with a host which can carve out this protected area for the execution of sensitive workloads. And we basically expect for a TEE to provide, at the minimum, the following capabilities. Memory confidentiality, so we want that memory to be encrypted. The host can't see what's going on. We also want integrity protection so that the host can't manipulate what's happening inside of that TEE. The third is that we want this to be focused on general compute. So we're not looking for, a lot of times TEEs are deployed as like you can put a little tiny bit of an application in there and protect just this one sensitive component. Our vision of TEEs are much more broader than this, and we view this as a generalized compute engine. So we want to be able to run full workloads inside of the TEE. The last thing is that it needs to provide its own hardware random number generator, because we can't trust the host to do random number generation. So for example, you can't just open dev random inside of a TEE and ask for random data, because the host could lie and then use that as a way to attack the TEE.
So that's great. So the tenant is going to want one of these TEEs, obviously, to run their workload in. But how do I know that what the host is offering me is actually a valid TEE? Because the core part of where we're coming from is that we just don't trust the host. The only bit of the host we trust is the CPU and associated firmware. So how can the host know that what is being offered to it is actually a valid TE? Well, the answer is there's a process called attestation. Now, this process varies quite significantly across different implementations of TEs, but basically allows the host to make a cryptographic measurement of the TE and prove to the tenant cryptographically, based on information already available to it, that what is being offered is a valid TE. Once that's happened, the tenant can take its workload, the code and the data, encrypt it, and basically get it pushed into the TEE in such a way that the host can't see it as it's going across the host, and no one else can see it either. Exactly how that happens is pretty complex, and this isn't the time to go into that. Very happy to discuss that on another occasion. Here's a slide about the different types of TEs and how they're different. Nathaniel?
Sure. So the industry has basically come up with two different ways of implementing TE. And the one on the left is what we are calling process-based. And basically, this allows you to carve out a subsection of a process that executes in the trusted environment. But you pretty much have direct access to the rest of the process from inside of the TEE, and through a set of calls across the layer. The two primary examples of this are Intel SGX, which is currently available in hardware, and you can currently get in quite a few clouds today. The drivers for it are not upstream, but they are currently going through the upstreaming process for the Linux kernel. And then RISC-V Sanctum is another implementation of this, which currently does not have any implementation in silicon. On the right-hand side, we have the virtual machine-based TEEs. And basically the way that these work is they extend the existing virtual machine boundaries, so we already know how to run virtual machines. And basically what they do is they encrypt that virtual machine and provide integrity protection for that virtual machine, as well as attestation for the contents of that virtual machine. So examples of this include AMD SEV, which is, again, like Intel SGX, widely available, especially in clouds. And there are a few others that are coming as well. IBM has announced PEF for power, although the hardware is not generally available yet. Intel has also made motions in this space with a technology called MKTME, which currently does not have any form of attestation. However, they did file a patent on adding attestation to MKTME. So we can probably expect to see further exploration in this space as well. There's also a few things that we do not consider to be TE. The first one is Trust Zone. Trust Zone is basically an ARM technology, and it allows you to, it works actually totally different than the others, in that there's a whole parallel operating system, and you can basically run a process inside that operating system, and you can communicate between it and the main operating system. The performance of it is not very good. The resource constraints are very onerous, so you get only a few megabytes of memory, and it's not served for generalized compute, which is our target. A second example of this is TPM. And although you can execute a little bit of code on TPM, it's not a CPU, so you're executing it in a specialized hardware environment that does not provide generalized compute. So it is not within the target of our trusted execution. Again, both of these because we're focusing on making this available to general compute and not just to specific small bits of technology. Mike?
Yeah, so done that. Let's talk a bit about what Enarx is and what it aims to do. We've given you a sort of baseline introduction to the technologies and kind of intimated about some of the things we want to do. So first of all, obviously, given we've just spent the last 50 minutes talking about TEs, we use TEs for our confidential workloads. We want to make it easy to develop and deploy, and we have some very strong design principles. If in doubt, we tend to go strong, and that doesn't make it always easy for us to write it, but we think it's the best option for people using it. Absolutely, we aim for it to be cloud native. So, we'd love to be integrating it over time with OpenShift, Kubernetes, and the rest. And the other thing is, it's of course completely open source. It's a project, not production ready yet, and it's actually part of the Confidential Computing Consortium, which is a Linux Foundation project aimed specifically at encouraging use of TEEs. So, where do we want it to be? What do we want the picture to look like? So this picture looks a little bit like the one we saw before, with a tenant on the right and the host and the TE on the left, with the attestation and the workload delivery. But here we introduce the idea of a keep. Enarx keep is where you run your workload. It is an instantiation of a TE. But importantly, very importantly, you, the user, should not care what the underlying hardware is, whether it's process-based, VM-based, Intel-based, AMD-based, or in the future, another silicon provider. So this is an intro to what the different layers that we are providing as part of Enarx are. Another good one for you to take over, I guess, Nathaniel.
Thanks, Mike. So at the bottom here, we have, like we've talked about, our two different types of keeps. We have process-based on the left and VM-based on the right. And these represent fundamentally different hardware technologies. So if you were to write an application using one of them today, it would not at all be portable to the other ones. And what we want to do is we want to abstract that away. And so we do that by providing a common runtime for applications. That common runtime is based on WebAssembly and WASI. WASI is the WebAssembly System Interface. These are W3C standards, and we are working with the W3C subcommittees in order to make sure that we get what we need there. But the idea is that you can write to these standards, and you do not need to rewrite an application, for Enarx specific things. You just use the existing standardized tooling. On top of those standards come language bindings, and these already exist today. So, for example, there's already a libc that uses WASI and can use WebAssembly underneath it. And then finally, an application on the top. This is the bit that actually gets deployed into the keep from the tenant. So the point is the application gets to write on top of its language bindings, and it should just mostly work. There are obviously going to be corner cases for things that aren't portable, and there's a few syscalls that can't be supported from libc, but otherwise it should be mostly possible to fairly trivially recompile your application to run inside this architecture.
So where we are right now is that we've done some of the bits, by which I mean we haven't done any of the WebAssembly or WASI pieces yet, but we've started work on providing the capability to run the same binary, and I mean exactly the same binary, not just the same source code, the same compiled binary with the same, if you take a hash of the file, it's exactly the same hash, the same binary, an ELF static pi binary on both architectures, on the Intel SGX and the AMD SEV. So fundamentally different approaches, which was meant lots of assembly language. I don't mean WebAssembly, I mean actually assembly language coding and some clever Rust stuff, which I've written none of at all on either case, I have to point out. But this is where we are right now. Nathaniel, do you want to give any extra visibility to this?
No, I think you've summarized it very well. This is one internal interface. We don't want to expose the static pi interface externally, because there's a lot of really difficult details to get right, and not all the platforms can support exactly the same thing. But we are using this for internal portability of our WebAssembly runtime, and it's a big milestone for us.
Absolutely. So this is where we want to be next, where we have implemented the other pieces on top, but the point is that they should be the same pieces on the left and on the right, because we have the same abstraction away on both SEV and SGX. Again, anything you want to add to that?
No, let's move on.
Well, that's kind of it. We've had 20 minutes or so to go. We used 20 minutes. Really, we want to say, come and join us. Come and have a look. All the code is open. We do all of our design work in the open. We have daily stand-ups, which are open to all. We advertise that on our wiki. Lots of information there. Everything's Apache 2.0. Everything pretty much is written in Rust with the odd bit of assembly language thrown in. And we'd love to see you. So let's move on and maybe move to some questions.
Yeah, do you want to go ahead and stop sharing your screen?
I believe I am now no longer sharing my screen.
Awesome. Okay. Okay, so we have a few questions from the audience. First, Alex wants to know, before you answer this, let me remind you, this is public Community Central. So this will go on the YouTube channel later on. So the first question from Alex is, this is one of the few projects at Red Hat that is written in Rust. What has been your experience with that ecosystem of tools, and are you happy with that decision?
Nathaniel.
Yeah, so I've written most of the Rust code in the project, so I think I'm probably the most apt to answer this question. Rust is both incredibly exciting, incredibly satisfying to work in, and oftentimes fairly difficult. One of the challenges that we have as the project is that we are actually writing a lot of different parts of code for different parts of the stack. So for standard user space applications, Rust is pretty easy to work in, gives you most of the functionality that you need, and works pretty well. But once you try to get down into things like writing a kernel in Rust, there are quite a few things where Rust shows its rough edges. That being said, overall, we're very satisfied with the decision, and we think that Rust provides us some promises around code stability, functionality, and safety that are incredibly important to us. So we are happy with that decision.
Great question.
Okay, next question from Nitesh. Are you using any specific hardware accelerator for offloading crypto operations?
This is a great question. Let me start on this, Nathaniel, and you can add some stuff if you want. So the answer to that is no. The TEs themselves provide the boundary of trust that we have. So we don't want to be using anything outside that. Now, if the CPU implements internally to the TE the ability to speed things up, that's great. And if at some point, crypto offload cards support the sort of trust model that we would need in order to use them, we'd certainly be very interested in that. There's been talk of maybe GPUs providing some of these trusted execution environments as well. We're not seeing any of that in the market yet, but it's been talked about. And that's another area of great interest as well, of course. So the answer is not yet, but it's a really good question. Nathaniel, anything you want to add to that?
Yeah, I just want to reiterate, really, it's very hard for external hardware to extend itself into the trust domain of the TEE. And it's also something that we kind of don't want. One of the things that we are focused on is we are focused on having a homogeneous environment across basically all different ways to deploy applications. And if you broach the TEE with specific hardware, then oftentimes you are tied to that specific hardware and your execution environment is no longer homogeneous, which severely limits your portability. So we think we can provide pretty good performance this way. Many CPUs do have built-in instructions for doing things like AES, which can certainly help. We know that that's not the same as all crypto offload. But really, this is about increasing trust, and crypto offload makes that very hard. And so we would prefer to err on the side of trust.
Loving these questions, by the way. They're great. Thank you. What's the next one, Josh?
Okay. Do TEs address or reduce the impact of CPU-level vulnerabilities like Spectre and Meltdown? This is Sam, who doesn't think so, but he wants to hear a discussion about it.
Yeah, it's actually sort of orthogonal. They do make it slightly harder to attack a system through something like Spectre and Meltdown, but no, the fundamental issues don't go away. And you can actually see this, for example, in SGX. There was a vulnerability called L1TF, and L1TF basically had some software patches, and you also had to disable hyperthreading in order to make it work well, work in a secure way on older CPUs. And we are now seeing CPU fixes for that at the silicon. So overall, we think that there is a lot of awareness in the industry about these kinds of issues. In fact, I don't think I've ever given a presentation on Enarx where this specific question has not been asked. To put that in perspective, CPU vendors know that this is a problem, and they are working very hard to address it. Ultimately, we think that over time this will be significantly reduced, and we're hoping not to have to do extensive mitigations in Enarx. Given that we're not production ready today, we have a little bit of time that we can play with that. But no, those fundamental questions of security surrounding things like Spectre and Meltdown don't go away, and we really need CPU vendors to step up and improve the game.
Cool. Okay. So next question is about TPM. Nitesh wants to know about hardware-based TPM versus software-based TPM.
Yeah, so we're not using TPMs at all. So maybe we weren't clear about that story in the slides and the presentation. TPM doesn't count as a TEE from our point of view, and therefore it's not something that we're interested in using. It's not something we consider specifically as part of the Enarx project.
Okay. Next question. Are there any plans in the Enarx project to specifically address multi-tenant use cases?
That's a
data
great
separation.
question.
So that's a great question, and it can actually mean multiple different things. So in terms of multi-tenant from the host perspective, yes, absolutely, we are multi-tenant from the host perspective. The idea is that you should be able to have a single physical system, and you should be able to run jobs from pretty much any tenant anywhere, and they can't interact with each other. That's sort of the whole point of what we're doing.
Very strong isolation, not just from the host, but from other tenants. So the standard design is you get one workload per keep, and therefore you get isolation. We're not having the standard isn't multiples. But Nathaniel?
Yeah, so the other kind of multi-tenancy is multi-tenancy within the keep. And in fact, this is one of the things that WebAssembly helps us with significantly, because we can do things. WebAssembly has a concept called zero trust linking, although I don't think anything is ever zero trust, but the notion of zero trust linking is essentially that you can take code from multiple different parties, run it inside of the same execution engine, and they can interact with each other, but they can't actually view each other's namespaces, they can't view each other's address space. And so you get this sort of strong isolation built in with WebAssembly. In particular, in the long term, we would like to be able to attest to multiple parties and allow multiple parties to deliver code into a keep. It's a little difficult with the hardware that we have today for a variety of reasons. But we have given that feedback to the hardware vendors precisely to make sure that we have that kind of operation in the future. As of today, we don't have any code for that, simply because we're still working on getting the single tenant case working. So I think that answers your question, or at least I hope it does.
Yep.
Cool. So next question, are there any plans for FIPS, for Phipps Compliance?
Absolutely.
We would. Yeah.
So one of the ideas behind Enarx is that you can deploy your application on Enarx, and that it solves a significant number of the Phipps compliance things for you out of the box. So that is something that we are very strongly targeting, and basically it's always in the back of our minds. Although we don't have a product yet, obviously that will need to go through certification and things like that in the future. But yes, it is absolutely on the roadmap.
Yeah, that's really important to a number of the sectors that we're targeting: public sector, banking, healthcare. So absolutely.
So Adam wants to know, what are the expected penalties or difficulties of using WASM on the next step?
Using WASM.
Our biggest difficulty right now is enablement of the hardware. SEV can work pretty well today. The drivers are in the upstream kernel and does require a little bit of configuration, but it mostly does work. SGX also does work, but it requires you to patch your kernel because the drivers aren't upstream yet. And so basically our current state of difficulty is just enabling these specific technologies. Beyond that, one of the big questions we have is going to be around how our project, the dependency that we use, WASM time, how that is going to actually interact with the syscalls. So, for example, in SGX, you don't get a different address space. You only have one address space that you can work in, and so we need to make sure that the syscalls can actually work in that case, and we may need to provide modifications to WASM time in order for that to work, but we haven't actually crossed that bridge yet. Overall, WASI, which if you remember was the WebAssembly System Interface, you can sort of think of that like POSIX. It's a subset of POSIX, and we believe that we can make most things work pretty well fairly easily. The biggest difficulty we're going to have is around file systems, because we can't just expose unencrypted files to the host. That breaks our trust model. So we're going to have to implement block encryption in a file system at some point. That's why we've pushed that to essentially our 2.0 release, because we think we can deliver some incremental value without file systems first and tackle that more difficult problem later on. But I think that answers the question.
Cool. Well, thank you. A much simpler question from Pete. Which Linux kernel version are you starting with?
Maybe Pete could clarify. I don't know if he's talking about on the host or on the guest. I'll answer both questions.
Why don't you just answer both?
Yeah, so on the host side, we are currently using a patched version of the Fedora 32 kernel, which is I think 5.7 or 5.6. And again, we need patches currently for both SGX and SEV. Although the SEV is a very trivial patch that's already been upstreamed, and we're going to hopefully backport it to the Fedora kernel. So in the guest side, we actually aren't using the Linux kernel at all. We're using a very tiny microkernel written in Rust that basically just performs it performs page table manipulation and proxies syscalls to the host to be executed on behalf of the guest. So it's many millions of lines less code than say a Linux kernel.
Okay, next one from Eric. I'm going to read this out loud because it's a complicated question. AMD SEV is hardware memory and CPU register state encryption, and as such completely transparent to the guest. So what do you mean by having to rewrite your application when porting to a different platform? Wasn't that supposed to be handled by WASI, which the consumers of Enarx should not care about?
That's exactly right. So basically, you shouldn't need to rewrite your application. That's exactly what we want to avoid. So you shouldn't care whether you're running on AMD or on SGX or any other future implementation of a TE, because we're abstracting that away. We are providing the WASI layer and the WASM layer, the WASM and the WASI layers, so that you don't need to rewrite your application. You just compile it for WASI, and you're done. You just shouldn't care at all. Sorry we weren't clear, but you've absolutely nailed the question on the head, Eric. That's one of the key things about making it as easy to deploy as possible. Is you just write to whatever it is, and then you compile to WASI.
One of the key points here we might point out about attempting to do this as a virtual machine. So SEV was designed to run a traditional operating system as a guest, and theoretically you don't need to port your application in that case as well. However, the software stack is really not there yet to provide the full functionality of SEV into the guest. For example, what you really need to do is you need to basically load the guest into memory. You need to then attest the memory state of that VM to the tenant. The tenant then establishes an encrypted channel all the way to the CPU to inject things like secrets into the guest. And then the guest boots, and it needs to pass those secrets from the BIOS down to the bootloader, down to the kernel, and probably insert them into the kernel keyring. None of that code exists today, and it will probably be a while before that code exists. This is one of the advantages of not using the traditional stack inside of the environment, is that we can iterate very rapidly because we have direct access to the hardware and only one component on the inside to deal with. So we are hoping to basically be able to deliver that functionality much faster than you will be able to see use of it in virtual machines.
I really hope you were hoping for a technical answer, because you got one.
Cool. Okay, last question, and then we will wind it up for the day. Alexi asks, TEs are confined to specific CPUs that they run on. Is there any potential towards multiprocessor scalability?
SEV does multiprocessor today. And SGX, that's a good question. I don't know that I actually know the answer to that. So yeah, maybe ask your Intel rep.
Okay. Well, thank you two very much for presenting this relatively new project to us. And that will wind up for Community Central for today. As always, this will be going on the Red Hat Community YouTube channel later on today. And please check the Community Central schedule linked from our YouTube channel for next week's presentations. And that is all for Tech Tuesday. Thank you.
Thanks, Josh.